Hello guys, as usual, stay home, stay safe, and do Excel chemistry. So today we're going to talk about the properties of colloids. Okay, so the various properties about the colloids. So let's talk about the properties of colloids. Basically, depending upon the various factors, we have the let's say, for example, we know that the particles size of the colloids ranges from 1 nm to 1000 nm, right? So if the size is bigger or if the size is smaller, or the size factor, basing upon the size factor we can find the different properties. So one important factor that we should study to know about the properties is depending upon the size, based on size. The other is based upon the size of the particles and movement of the particles, and third one is regarding the charge that is developed on the particles, and fourth, you can talk about the number of particles involved, dependence on the number of particles. And there is also one more one, that is the color factor. Okay, so basing upon these five, we'll study about the properties. Fine. The size of the particles is, now putting it short, I can say that this refers to the optical properties. Okay, and movement of particles, this refers to the kinetic, right? Movement refers to what? Kinetical energy or kinetics. So I name them as kinetic properties. Charge on particles, I'll write it as electrical properties. And number of particles, based upon the number of particles, colligative properties. If we had studied about the solution chapter, you must be familiar with this, but just because we have come to surface chemistry, I'm just introducing the term. In detail of this point of colligative properties, we will study in depth in the solutions chapter. And color as it is. So these are the five based on the things that we will be studying about the properties of colloids. So starting with the first one, that is size of the particles. So I'll write it as based on size of the particles, we call it as optical properties, and so on and so. Fine. So let's start with the size of the particles. So as I say, size, that is optical properties, we'll talk about a very important effect, something, and you are familiar with this word, that is Tyndall effect. Okay, so what is this Tyndall effect? For example, let me show. All right, yeah, I'll show like this. Actually, I tried to show that Tyndall effect, but it is not working. If it was a virtual class, sorry, if it was our face-to-face classroom, it would be more easy. Anyways, rather than showing and all, maybe I can make you visualize certain things. For example, all of you have watched movies, right, in theaters, right? So when you have been to movies, you can see that from the projector. Okay, suppose if the screen is here and the projector is somewhere here, fine, the projector room, from here you can see the rays of that coming, right? In even in movies also they show, like if a bottle is placed here, then we can see the bottle. So in other words, from the projector we see that the path of this light can be clearly seen from sitting here. Okay, you can see that. Okay, next time when you go, if anybody, I think all of you have seen it, but in case if you have not seen, if you have not observed, next time when you go to the theater, do observe this, from the projector the rays coming out. Okay, now the rays, the particles, you can see the path of the light. Fine, you can see the path of the light. This is because of Tyndall effect. Okay, so writing in short, what is Tyndall effect? We say that when the light is passed through the colloidal solution, the path of light is visible. The path of light is visible. This effect is called as, this phenomena is called as Tyndall effect. Okay, so what is Tyndall effect? Very simple. We can see the path of the light when the light is subjected or passed through the colloidal sol. Now in the theater, what is the colloidal solution? Is the theater is full of the dust particles, or you can say the air itself acts as a colloidal solution, right? So the rays of the projector passes through the colloidal solution, and then it hits the screen, and that's the reason you can see from sitting here, you can see the conical, see what is the shape of this one, the cone shape, right? So in fact, you call this cone as Tyndall cone. Tyndall cone. Okay, so why does this Tyndall effect occurs? The reason for the Tyndall effect is a simple one, that is scattering of light. Scattering of light by the colloidal particles. What happens? What exactly happens is this. See, suppose, let me draw a picture so that, for example, let's say I have a solution of colloidal. This is my dp, and in this dp I have the dm, and dp particles have been dispersed. Okay, so suppose when I have a light source, let's say like I have the torch over here. Okay, so this is my source of light, and from here when the light is passed through this colloidal solution, okay, the light exactly, okay, converges and then diverges. We know what exactly in physics you might be studying about this phenomena and all, that is scattering of light. Fine. So when this light which is passed through, so this light or this region, when we see from the top from a microscope, okay, somewhere, so suppose let's say like this is what we are looking from the microscope, and now, so from this view what we observe here is the scattered, okay, from here the particles that are there scatters the light in all directions. Okay, so when this light which is scattered, and this cone that we observed, which I was telling as the Tyndall cone, this cone, we will observe that the light that has been scattered is in blue color. Okay, so why blue? Same thing can be explained. The sky is blue at daytime, okay, but in the early mornings or in the early evenings you will find that the sky is orange or red, something like that, right? Now same explanation here also. What exactly happens is when the light rays are passing through, and when it hits the that is obstacle of colloid, so the light rays which is hitting the obstacle has to happen, either it should be transmitted or it should be reflected. Okay, so when we observe from the angle of 90 degrees, okay, the reflected point, okay, so from the reflected point when you observe, like the source direction is, the torch direction is this, and when we are observing from this angle, so which is an angle of 90 degrees or the reflection point, then we see that a blue color is observed. Suppose if we observe from the transmitted angle or transmitted point, then it looks red in color. Okay, so now the point, the summarizing the things, in the presence of sunlight, in the presence of the source, that is light, when it is passed through the colloidal solution, we see a cone shape which is called as Tyndall cone, and we also say that the path of light is visible. If this was a true solution, you cannot see the path of light. Okay, you maybe you can try at home also. Take water, in a glass of water, take a glass of water and put some milk or curd in it and stir it, and then take a torch, and through that light of the torch, you just put that glass of water with milk, and you will find that you can see the beam. Okay, you can clearly see it, the cone. Fine. Now why is that? Is this reason. Fine. And one more point, when we look at an angle of 90 degrees with respect to the source incident ray, when you look at an angle of 90 degrees, we observe that the color of the cone or the color of the light is what? Blue color. Okay, so let me write the point. So this is what my what I can call it as reflected point of view, and if I observe from here, that is transmitted point of view, I will see the color as red, and from here I will see the color as blue. Okay, blue color. Fine. So this is my incident ray. When observed at an angle of 90 with respect to incident ray, we observe blue color. Alright, fine. So this phenomena is called as Tyndall effect, and the reason why the Tyndall effect is what? Scattering. Okay, you know, like the rays have been scattered in all directions. Fine. From this angle, don't say like from this angle only we will see the that is the Tyndall effect or the blue color only. No, from here we can see the blue color. From different angles we will see the different colors. Okay, nevertheless, same thing in like as I said earlier, in the early mornings or in the evenings, what you see is the sky is red or orange in color, but in the daytime what you observe is what? Blue in color, because of scattering of light again. Fine, in physics you might have studied the same point. Okay, so one more example I can give is what? Milk. Okay, so suppose if you have the milk, when you are observing from angle of the incident, from the angle it is 90 degrees and it is the reflected point, the milk appears blue, and from the transmitted point, if you see from the transmitted point, you see right red in color. Okay, so this is what my incident rays. Okay, all right. Now what are the conditions? We have understood what is Tyndall effect, and we have understood why Tyndall effect is happening. And now let's understand how the Tyndall effect will happen, or what are the conditions of when the Tyndall effect will happen. Tyndall effect can happen. Two important factors in 2017, I hope there was a question from this area. Okay, number one condition, let me write it as conditions. Conditions to show Tyndall effect is this: the wavelength of the incident light should be approximately to the size of the particles. Size, I mean the diameter of the particles. What do I mean with this? I mean, see the incident ray. See, this is what the incident ray. This ray, when I say it's a ray, that means it will be having some wavelength. That wavelength of this incident ray must be approximately equal to the size of the particles. In other words, the wavelength and the size of the particles should not have huge variation. What happens if there is a huge variation? Suppose if the particles are so small, and the wavelength is higher, then it cannot even hit the surface and the scattering cannot happen, and no scattering, no Tyndall effect. Understood? And there is another condition, that is the difference between the refractive index of dp and dm should be large. What do I mean by this? See, the scattering of light, visibility of the scattering of light is only seen or is only observed when only the refractive index is of different refractive index. Okay, you might have studied about the Snell's law and all, right? So if the refractive index is of same, if there is no variation in the refractive index, then we cannot appreciably see the scattering of light. Okay, so that's another condition. The difference between the refractive index of dp and dm should be large. The difference should be large. And one more important point is this is not a condition, but I would say, like, important point is, we generally observe or we generally see the Tyndall effect in lyophobic sols, okay, and less in lyophilic sols. Now why? Already I told you, like, in lyophilic sols, what happens, there is a force of attractions between the dm and dp. That forces of attraction between dm and dp causes, or that forces of attraction may cause the refractive indexes to be minimized. Are you understanding? So because of this, we cannot appreciably see, excuse me. Alright, so bottom line is this, that excuse me. So lyophilic sols, we will find that the Tyndall effect, the observation of Tyndall effect is very less because of the forces of attraction between dp and dm. Okay, so on a whole, Tyndall effect is this. Alright, so let's move to the next property, that is the second one, that is kinetic properties. Okay, so we talk about Brownian movement. Okay, so what is this Brownian movement? You might have studied about this many a times, even in 9th standard, right? So same thing, but a little more information is there. So first, number one, by definition, what is Brownian movement? The random zigzag movement. The random zigzag movement of colloid particles is called Brownian movement. Very simple. Okay, now see, for example, the particles, that is the colloidal particles, they keep moving in random directions. Fine. So why do they keep moving in random directions? Because they hits the surfaces of, or they come in contact with the dm molecules. The dp molecule, they come in contact. See, suppose if the motion is in direction and the dm particle is here, so it strikes this and then it changes its direction. So like this random movement, okay, there is no particular direction all through. Okay, so it's a random movement. So the random zigzag movement of colloidal particles is called as Brownian movement. And now again, why does this happen? The reason is because of the continuous collisions between dp and dm. So the reason is what? Due to continuous collision between the dp and dm. Okay, then are there any conditions? I don't say conditions, but we have to know some important points in it. So let me write like this. Number one, it happens in all colloids. We observe the Brownian moment in all kinds of colloids. Then the colloids, okay, that is the Brownian moment depends upon the size of the particles and viscosity. Okay, let me write that. It depends on, the Brownian moment depends on the size of the particle, the size of the particles and viscosity of solution. Viscosity of solution. So if at all I have a smaller size particles and it is having, suppose let's say viscosity is very less, so what will happen, the movement, okay, smaller size and viscous, very less viscous, so what do you expect, the smaller size and very less viscous particles, they move fastly or they move slowly? As said, smaller size and viscosity is very less. If viscosity is more, then the viscosity is nothing but the opposite force of movement, right? Just like in friction, you study in fluids viscosity. Fine. So now I am saying that it is less viscous. If I say less viscous, the movement should be fast or slow? Ultimately, it should be faster. So I write it that if small sized or small size and less viscous, the movement is fast, right? Is fast in the motion of the like the particles will be fast in the motion, right? All right. So what else? Yeah, one important point, one more, that is as temperature increases, what do you expect? As temperature increases, the Brownian moment should dash. Common sense. More the temperature, particles gains the energy, and the molecules or the particles which has sufficient energy, will they restrict to a place or keep randomly moving? Randomly moving, and randomly moving is nothing but the zigzag movement, that is Brownian moment. So as the temperature increases, the Brownian moment should increase. Okay, so that's all about the Brownian moment, nothing much. Okay, so so for this, let's stop with these two properties only. In the next video I'll talk about the electrical properties, which is very important. So I'm taking a pause here itself. Okay, all right.